الحمد لله رب العالمين والصلاة والسلام على أشرف المرسلين وعلى آله وصحبه أجمعين. Water requirements, sources, health hazards, purification, sanitary specifications by Professor Mahmoud Hani Sulaiman. Man can survive for 5 weeks without food, but not more than 5 days without water. Water is essential and the predominant constituent of cell protoplasm, so 70% of body weight is due to water only. Water has influence on health and life, directly and indirectly. It is related directly because water is essential for digestion, regulation of body temperature, removal of wastes from body through tears, perspiration, urine, and feces, and for lubricating joints. It also acts as a buffer by neutralizing acids inside the body. Moreover, it is a necessary vehicle for all metabolic processes in body. Deficiency of water in body causes dehydration, acidosis, shock, urinary tract infections, indigestion, and constipation. Daily requirement of water for drinking purposes is about 2.5 liters. Daily requirement about 2.5 liters. Consumption of water 2 to 3 times the actual requirement is also not harmful. Therefore, it is always advisable to drink as much water as we can. Water has influence on health of human indirectly also. It acts as a vehicle for transmission of many communicable diseases like typhoid, diarrheal diseases, viral hepatitis A, poliomyelitis. Water constitutes breeding place for mosquitoes, which transmit disease to humans as malaria, filaria, Japanese encephalitis, dengue fever, etc. Man also needs water for domestic purposes as cooking, washing clothes, cleaning utensils, gardening, and above all for drinking. He also needs it for commercial, industrial, and recreational purposes. Since water has influence on health of individual, it should be of good quality. Water for drinking purposes must be safe and wholesome. A safe and wholesome water is one of which is the following: free from pathogens, free from harmful chemical substances, pleasant to taste, i.e. free from odor and color, usable for domestic purposes, so free from pathogens, free from harmful chemicals, pleasant to taste, usable for domestic purposes. Water is contaminated, i.e. contains pathogens or harmful chemical substances. Polluted, i.e. contain impurities affecting physical quality of water as color, odor, taste, and turbidity. Groundwater appears as springs, i.e. flowing surface water. In nature exists as a continuous water cycle involving stages of evaporation, precipitation, runoff, percolation, transpiration. In this cycle, water becomes materially changed and becomes contaminated or polluted. Compared to rainwater and surface waters, groundwater, subsoil water, is safe for drinking purposes due to ground acts as a filtering medium. This is the impurities of water and their types. Impurities of water either dissolved or suspended. The suspended ones either organic or inorganic. Inorganic are inorganic particles of clay, slate, mud, radioactive material, etc. Organic suspended impurities are vegetable origin, leaves, algae, peat, and animal origin, living organisms. Dissolved impurities either Gases or solids. Gases as chlorine, ammonia, nitrogen, carbon dioxide, hydrogen sulfide, etc. Solids as inorganic salts of calcium, magnesium, sodium, iron, manganese, zinc, and so on. Salts are oxides, sulfate, and phosphate. Organic decomposed vegetable matter, algae, weeds, etc. And animal matter, worms. This picture shows sources of groundwater contamination. I put it here so you can see how many are sources for contamination of groundwater, and good effort must be done to prevent them. From left to right: pesticides and fertilizers, accidental spills, highway de-icing salts, septic tank, cesspool, drinking water, this is the well, landfill dump of refuse pile, waste lagoon or pond, gasoline station, oil well, industrial disposal well, and coal strip mine runoff. Merits of groundwater: free from pathogens and harmful chemicals, does not require purification, available even during summer season. Demerits of groundwater: mineral content is high, making the water hard, requires certain arrangements like pump to lift water. The usual source of groundwater are wells and springs. Well, it is an artificial pit or hole sunk into the earth to reach subsoil water. Different types of wells are shallow well, deep well, artesian well. Shallow well, deep well, artesian well. According to method of construction, wells are also classified into dug wells and tube wells. Shallow well, please print and read. At the lower page, pollution can be detected by introducing a solution of fluorescein and caustic soda in this area, and by examining water at different times for the testing material. Shallow and deep well, print and read. Deep well or driven well, print and read. Artesian well, irtwazi, print and read. And this is a scheme for this artesian well. Sanitary well, read. This is the scheme for sanitary well, showing parts of this well. Sanitary well continued, please read. Cover, hand pump, cleanliness. This is important. Health hazards of water contamination. These are classified into two broad groups: biological and chemical hazards. Biological and chemical hazards. This is to show you a waste treatment facility. It is complicated and its cost is high, expensive. This is to show you septic system. Consists of septic tank and an absorption field. This system is commonly used to treat domestic wastewater in suburban and rural areas. Also, it costs much to treat water. Biological hazards. These are the classical waterborne diseases caused by presence of an infective agent or an aquatic host in water. It is either those caused by presence of infective agents, viral diseases, bacterial diseases, protozoal diseases, helminthic diseases, leptospiral disease. Viral disease: viral hepatitis A, E, poliomyelitis, rotavirus, diarrhea. Bacterial diseases: typhoid, paratyphoid fever, bacillary dysentery, E. coli, diarrhea, and cholera, protozoal disease, amoebiasis, and giardiasis, helminthic diseases, ascariasis, enterobiasis, trichuriasis, hydatid disease, leptospiral disease, Weil's disease. B. Those caused by presence of aquatic hosts, snail, schistosomiasis, cyclops, fish tapeworm disease, Hymenolopus diminuta. Chemical hazards of water. These are non-specific waterborne diseases. These occur due to presence of certain harmful substances or due to presence of higher or lower concentration in water as follows: deficiency of fluoride, deficiency of iodine, sulfates and chlorides, lead, iron, zinc, excess of lead, mica. Deficiency of fluoride lesser than 1 mg per liter will lead to dental caries, and excess of fluoride will lead to dental fluorosis among children and skeletal fluorosis among adults and elderly. First is fluoride. Second, deficiency of iodine, goiter. Excess nitrates, deficiency of iodine will lead to goiter. Excess of nitrates, more than 45 mg per liter, will lead to cyanosis among infants, i.e. infantile methemoglobinemia. The dissolved organic impurities like sulfates and chlorides causes diarrhea, gastric disturbances like dyspepsia. The salts of lead, iron, and zinc will lead to constipation and colicky abdomen. Excessive lead will lead to lead poisoning. Inorganic suspended impurities as mica will lead to diarrhea. Hardness of water. Hardness is unsuitable for boilers and industry. However, it appears to have a beneficial effect against CVDs, cardiovascular disease, other water-associated disease or hazards resulting from contact with water are infections of eyes, ears, nose, throat, vulvovaginitis, ringworm infections of food. Disease transmitted due to inadequate use of water are shigellosis, trachoma, conjunctivitis, and scabies. Other group of diseases related to water are mosquito-borne disease, because water is the breeding place for mosquitoes. Purification of water. The purpose is to produce hygienic, safe, and aesthetically pleasing water. This can be studied under two headings: large-scale purification, small-scale purification. Purification of water on large scale. This is required for towns and cities. It is done in 3 steps: storage, filtration, and chlorination. Storage. Raw water drawn from rivers, canals, lakes, ponds, stored in concrete storage tanks, sedimentation tanks, where suspended impurities settle down by gravity and water is purified little by natural physical means. Water stored for 1 to 2 days and purified chemically also by aerobic bacteria oxidize organic matter with help of dissolved oxygen. Water purified little biologically by natural death of pathogens. Thus, water is purified physically, chemically, and biologically to some extent. Filtration. This is the second step of water purification, done mainly to remove pathogens and to some suspended impurities which have escaped in storage. Effective filtering media is sand. There are 2 types of filters: slow sand filters and rapid sand filters. Slow sand filters, also called biological filters, first used in England in 1804 and based on observation that muddy water percolating through earth came out on a hillside in clear stream. Later usage spread in the world. This method was adopted when coagulation process of water was unknown and spread of waterborne disease due to microorganisms were not yet discovered. Slow sand filters required vast area and so constructed outside city limits below ground to a depth of 4 meters. Slow sand filters continued. Please read this. This is a scheme diagrammatic section of slow sand filter. Above is the water and there is fine sand, coarse sand and gravel. Continued slow sand filters. Please read. To start with, filter acts as mechanical, but in 2 to 3 days, surface of sand bed gets covered with a slimy, greenish, jelly-like layer known as vital layer or the glial layer or biological layer. This is the most important name, biological layer. This is important, which is composed of algae, planktons, fungi, and diatoms. This layer purifies water by chemical and biological processes. The formation of this layer is known as ripening of filter. The effective filtration starts only after ripening of the filter. The effective filtration starts only after ripening of the filter. The auxiliary layer or biological layer absorbs colloidal particles, arrests pathogens, oxidizes organic matter and ammoniacal substances, thoroughly killing pathogens. Bleach color partially by removing color-producing substances and absorbs carbon dioxide, nitrates, and phosphates. Important. Water becomes bacteria-free. Thus, the biological layer is considered at the heart of the filter. Until this layer is formed, water is run to waste. Rate of filtration of water is 0.1 to 0.4 squared cubic meter per hour per meter squared area of sand and bed surface. 99.9% of bacteria are removed. Filtered water drained by under drainage pipes. Cleaning of the filter bed. Please read. Thus, filter is rebuilt once every 3 years. Advantage of slow sand filters. Read. Disadvantages of slow sand filters. Read. Rapid sand filters. Read. Two types of rapid sand filters. Gravity filters. This is the rapid sand filter scheme. Please read. The rate of filtration is in rapid sand filter is 5 to 15 cubic meter per meter square area per hour. Aeration. Water is first run through fountains so that oxygen of air mixes with water and partially removes taste and odor producing compounds and oxidizes iron and manganese. Meanwhile, carbon dioxide and hydrogen sulfide are removed. Coagulation and rapid mixing. Raw water is allowed to pass through a mixing chamber wherein water mixes with coagulant, alum, dose varying from 5 to 40 milligrams per liter. Flocculation, sedimentation. The water is then flown to next chamber wherein water is detained for 5 to 6 hours. During this period, aluminum hydroxide follicles entangle bacteria, colloidal particles, coloring matters, algae, fungi, and settle down at bottom of the chamber to form sludge. The supernatant water is then flown to rapid sand filters. Filtration, please read this. Cleaning, please read this. This is the section of a candy single bed pressure filter. Read it. Advantage of rapid sand filters. Disadvantage of rapid sand filters. Modified filters. Read it. Chlorination. This is the process of disinfection of water by adding chlorine as a final step in purification of water following filtration. This serves as final barrier to any pathogenic organism. Exposure to 60 parts per million in air for 30 minutes is dangerous, and to 1000 parts per million produces this within few minutes. Chlorine is an effective disinfectant, deodorant, and oxidizing agent. As disinfectant, it destroys almost all the pathogens present in water. However, it has no effect on spores, ova, cysts, and certain viruses like polio virus, hepatitis A virus, except in high concentration. It acts as deodorant by destroying algae and fungi. As an oxidizing agent, it oxidizes organic substances like excreta, sewage, etc. It also oxidizes ammoniacal substances. It also oxidizes iron, manganese, and hydrogen sulfide. Please read this about gaseous form of chlorine and liquid form chloramines. Solid forms of chlorine in form of solid chlorine is available in three forms: monohypochlorite of calcium, dihypochlorite of calcium, high test hypochlorite. Monohypochlorite of calcium, dihypochlorite of calcium, high test hypochlorite. Monohypochlorite calcium, classical bleaching powder. It is chlorinated lime or oxychloride of lime, prepared by passing chlorine gas over hydrated lime. It is an amorphous, hygroscopic white powder having chlorine smell. It readily absorbs moisture and carbon dioxide from air and releases chlorine. Thus, bleaching powder is an unstable compound. Fresh bleaching powder contains 33.3% available chlorine. The entire chlorine content is lost over a period of 3 months. Therefore, bleaching powder should be stored in brown-colored bottles with airtight lids and placed in cool, dry, and dark place to decrease its deterioration. Older sample of bleaching powder, lesser will be chlorine content. Roughly 2.5 grams of bleaching powder is required to disinfect 1000 liters of water. Bleaching powder releases chlorine, which acts as a disinfectant. It releases nascent oxygen, which oxidizes organic and ammoniacal substances. Chlorine of bleaching powder combines with ammonia of water, leading to chloramine, which controls algae and fungi and prevents development of bad odor and taste. Calcium oxide of bleaching powder acts as a bleaching agent and therefore used in paper and textile industries. Thus, bleaching powder is a disinfectant, deodorant, oxidizing agent, and a bleaching agent as well. Bleaching powder is widely used for disinfection of water for drinking purposes and to disinfect sputum, saliva, and excreta of infected patients. 50 grams of 8% strength chlorine bleaching powder is required for 1 liter of feces and urine. Loss of chlorine from bleaching powder can be decreased by adding excess of lime to bleaching powder in ratio of 4:1, which stabilizes chlorine content of bleaching powder. Such mixture is known as stabilized bleach, which are sold in market as petchlor or penchlor. The stabilized bleaching powder retains its potency up to 1 year. Dihypochlorite of calcium. This contains twice as much available chlorine. It has less tendency to lose its chlorine content on exposure to air. High test hypochlorite perchlorone. It is also calcium compound, provides 75% available chlorine. It is highly stable than bleaching powder, so it is purer form of bleaching powder. Perchlorone contains 70% available chlorine. Dose is 1 gram per 1000 liters of water. Deterioration of chlorine is very less on storage solutions prepared from perchlorone, also used for water disinfection. Action of chlorine. When chlorine added to water, it hydrolyzes immediately and completely into hydrochloric acid. Hypochlorous acids. The HCl is neutralized by alkali present in water, and the hypochlorous acid ionizes to form hydrogen ions, and hypochlorite ions as follows. The amount of ionization is governed by pH and temperature of water. Low temperature and high pH reduces efficiency of chlorine. Disinfecting action of chlorine is mainly due to hypochlorous acid and to a small extent due to hypochlorite ions. Chlorine acts best as a disinfectant when pH of water is around 7. If pH of water increased, hypochlorous acid very soon gets ionized to hypochlorite ions. Therapy, it is not available as a disinfectant. Disinfecting action of hypochlorous acid is rapid but short-lived. Principles of chlorination. Following are the principles. Water to be chlorinated should be clear, free from turbidity. Chlorine demand of water should be estimated. It equals amount of chlorine demanded by water for its purification equal to destruction of pathogens and oxidation of organic and ammoniacal substances. It is estimated indirectly by calculating difference between amount of chlorine added to the water and amount of residual chlorine remaining at end of contact period, because there is no practical method of determining beforehand the quantity of chlorine required to purify a certain volume of water, except by actually adding chlorine and testing water for free residual chlorine. Breakpoint chlorination. The point at which chlorine demand is met. If chlorine is added beyond breakpoint, it remains in free state as free chlorine or free residual chlorine. As chlorine is added, it combines with ammonia to form chloramine. This is combined residual chlorine. This is bactericidal. Peaking coincides with oxidation of all organic matter. Addition of further chlorine oxidizes ammoniacal compounds. Then addition of chlorine will lead to destruction of chloramine and release of free residual chlorine. Point when chlorine demand is met and free residual chlorine starts appearing in water is the breakpoint chlorination. Chlorine combined with ammonia is combined residual chlorine, and chlorine released after breakpoint chlorination is free residual chlorine. This figure shows or explains what we have said. Here is the destruction of chlorine by reducing compound. Here is the formation of chloro-organic compounds and chloramines. The combined is increasing. Here is the destruction of chloramines and chloro-organic compounds. Here is the formation of free chlorine and the presence of chloro-organic compounds not destroyed, free residual chlorine. Here is the combined residual and the breakpoint chlorination. Contact period is the period time required for chlorine to disinfect water. For optimum disinfection, presence of free chlorine for a contact period of 1 hour is essential. Presence of free chlorine for a contact period of 1 hour is essential. The free chlorine that remains at end of 1 hour is called free residual chlorine after breakpoint chlorination. Minimum concentration of free residual chlorine for drinking purposes in drinking water should be 0.5 mg per liter, i.e. 0.5 part per million equals part per million of water. 1 mg of chlorine in 1 liter of water provided 1 part per million concentration of chlorine. 1 mg of chlorine in 1 liter of water provides 1 part per million concentration of chlorine. The purpose of providing free residual chlorine in drinking water is to provide a margin of safety against further contamination of water, which is likely to occur during storage and distribution. Applied chlorine dosage. It is the correct dose of chlorine required to disinfect water so as to get free residual chlorine concentration of 0.5 mg per liter. This is also called as marginal chlorination, simple chlorination. It is sum of chlorine demand of specific water plus free residual chlorine of 0.5 mg per liter, i.e. dose required for breakpoint chlorination plus marginal chlorination as to get fraction of 0.5 milligram per liter. Superchlorination, process of chlorination wherein double usual dose of chlorine is added to water as to get fraction of more than 2 parts per million at end of contact period. This is resorted to when water is heavily contaminated or when there is threatening outbreak of waterborne epidemic. But the disadvantage is that such superchlorinated water will have smell of chlorine and it irritates throat, nose, and eyes while drinking. This table shows the recommended contact period of residual chlorine and level of free residual chlorine. This is the residual chlorine level and this is the contact period for drinking water, for water bodies post-disaster, and for swimming pool sanitation. For swimming pool sanitation, it is the maximum. Dechlorination, removal of excess of chlorine by controlled addition of reducing substances as sulfur dioxide, sodium sulfite, sodium bisulfite, sodium thiosulfite, or activated carbon. The fraction is reduced to less than 2 parts per million. Water on large scale can also be purified by using ozone and ultraviolet radiation. Ozonization, passing ozonized air through water. Ozone is an unstable gas. It is a powerful oxidizing agent. It destroys pathogens including viruses, destroys phenolic substances, producing a bad color, odor, and taste. Limitation of this process: ozone gas does not persist in water in free residual form unlike chlorine gas. Also, it has electrical and engineering difficulties. It is expensive. Since ozone also destroys undesirable organochlorine compounds produced after chlorination of water, ozonization and chlorination of water is now thought to be complementary processes for water purification. Dose of ozone is 0.2 to 1.5 milligram per liter of water. Ultraviolet radiation, this is for you to read. Purification of water on a small scale, either household purification of water and disinfection of wells. Physical methods of small-scale purification: first, boiling, then ozonation explained, and UV radiation explained. For you to read. Chemical methods: bleaching powder, high-test hypochlorite mentioned before, and here read. Chlorine tablets, quite costly, chlorine solution, for you to read and use if you are abroad from purified water. Iodine, for you to read. Don't forget Nesfil tablets, for you to read and use. Potassium permanganate, for you to read. Mechanical methods: either Pasteur-Chamberlain filter and Bergfeld filter, for you to read. وفي النهاية أقول الحمد لله رب العالمين, و thank you for your good listening.